Hello, my name is DDavis. I'm an acoustics consultant from Australia. This is a paper that I presented in 2017 at the Australian Acoustical Society's annual conference called Acoustics 2017, Sound, Science and Society. It was held in Perth. The paper is on a method that I've developed on how to maximize the size of an operating fleet of a site that has many noise sources that are time varying noise sources, and how to comply with the noise limits for a desired percentage of the time. Now, the types of sites that have time varying noise sources are, for instance, mines and quarries and construction sites. And the characteristics of those kinds of sites are that there are multiple noise sources that are operating simultaneously. There's usually a mix of stationary and mobile equipment. And those kinds of sites usually want to maximize their productivity, which means they want to maximize the number of pieces of plant and equipment that they can operate at any time. They also want to comply with their noise limits. Well, one of the ways that they can try to achieve that is by using optimization techniques. So we have to ask, what is optimization? It's either achieving the best possible result with limited resources, or it's achieving a desired result using the minimum resources, or it's achieving the best compromise between those two things. So it's helpful if we also define what optimization is not. It is not a designer using their personal preference, which usually is their favorite solutions for different problems. It is not when a designer uses their intuition to come up with a design. And it is not with the designer using a manual trial and error approach. Now, the types of noise sources that you get on sites such as mines and quarries and construction sites, they usually only have two types of noise emission profiles. Either they're making noise or they're not, which means that the noise source is either on or off. So there's only two options really per noise source. And just to give you some context, if you had 6 noise sources and each one had 2 options, either on or off, then there would be 64 possible combinations of noise sources being on or off. If there's 10 noise sources, then you'd have over 1,000 possible combinations. 30 noise sources, there'd be over 1 billion, and so on. If you had 100 noise sources, there would be an extremely large number of possible combinations of noise sources being on or off. Now, it's not possible to build that many noise models. You need a good way to search through the solution space. So you need to be able to come up with very good options, which means close to the best. Now, the optimization method that I've chosen for this paper to show one of the methods that we could use is the Evolutionary Algorithm. But we're using a slightly advanced version of it where we actually allow the variables to be uncertain. So we are using the Monte Carlo method merged with the ordinary evolutionary algorithm. One of the reasons why the evolutionary algorithm is particularly good for this kind of situation is that it allows variables to be on and off. So we can set up our problem with any number of noise sources, and the evolutionary algorithm will be able to cycle through a vast number of options of possibilities where some of the noise sources are on and some of them are off. So if we have a noise source that has a sound power level of 120 decibels and it reduces the sound energy as it travels through space until it gets to the receiver, where its received sound pressure level is 45 decibels, then that one noise source might be complying with the noise limit. But when you consider the contribution from all of the noise sources, the sum total of their contributions at the receiver might add up to a number which is higher than the noise limit. And then we have to consider the other complexity whereby the sound emissions from that noise source might be varying in time. So as the sound power level of the noise source changes in time, the sound pressure level at the receiver will also change in time correspondingly. Now, if the noise emissions from a noise source are changing with time, then the noise levels received at the receiver will also change with time. The amount that they change at the receiver won't quite be the same as the amount that they change at the source, because different frequencies of sound are attenuated by different amounts as they travel through space from the source to the receiver. But in general, the changing of the sound at the source will generally match the changing of the sound at the receiver. Now, if each noise source is changing in time, then the received sound at the receiver will also be changing in time, of course. So it's fairly easy to understand that if the noise emissions from a noise source are changing, then the noise levels received at each receiver from that noise source will also be changing. Now, one of the ways that you can plot statistics is with a box and whisker chart. So, for instance, if sound source number 1 has a maximum sound power level and a minimum sound power level as its noise emissions change with time, then the range of sound emissions from that noise source would be that, and the 50th percentile or the average would be that, and the quartiles, so the 25th percentile and the 75th percentile would be that and that. So each noise source has a different average sound power level, and each has a different range depending on how variable its noise emissions are. So the noise emissions from the site are now going to be the statistical combination of these individual noise sources. So if the noise emissions from a source have a statistical distribution and that sound has to propagate to the receivers, then the received sound pressure levels at the receivers will also have a statistical distribution. It will be slightly different because different frequencies get attenuated at different rates through space, but generally it will follow a similar pattern. different kinds of noise sources will have different kinds of operating patterns, and so the statistical distribution of the noise sources will be different for every single source. And these are just some of the typical kinds of statistical distributions that you see from different kinds of statistics, and it's entirely feasible that different kinds of noise sources could have any of these, or even something completely unique to that individual machine. Now, not only is there variability in the noise emissions from the noise source, there's also variability in the sound as it travels from the source to the receiver. So as the noise travels through the atmosphere, it can be refracted, it can be reflected, it can be absorbed, it can be scattered by turbulence, it can be diffracted around objects, it could be absorbed by the ground. And these things can be described statistically as well. So the statistical distribution of sound emissions from the noise sources and the statistical distribution of the propagation of the sound as it travels from the noise sources to the receivers gives a total statistical distribution of the sound as it gets received at the receivers. So the variability of the sound emissions from the sound source and the variability of the propagation attenuation as the sound travels from the source to the receiver will add together so that the variability of sound received at the receiver will be equal to the sum of those two variabilities. So the variability will be greater than either of the two input variabilities. So if we plot the distribution of the received sound pressure level, and we also show how much of that distribution is due to the variability in the propagation attenuation, then we can see that it's a two-dimensional probability. And if you consider each one of these dots to be one possibility, one sample, one moment in time, then the 99th percentile would be the line where 99% of these blue dots are on the left-hand side of the line, and the 95th percentile would be the line where 95% of these blue dots are on the left-hand side of that line, and the 90th percentile similarly. So now we can wrap it all together. So if the received sound pressure level at receiver 1 from source number 1 was this range, and the received sound pressure level at receiver 2 from source number 1 is this range, then you can see that if we turn noise sources on and off individually, then the range of received sound pressure levels received at the different receivers will also change. So the maximum, the minimum, the 50th, all of the percentiles, the 50th percentile, the 99th percentile, 95th and 90th percentile, they will all change as we turn individual noise sources on and off. So if we do that, if we turn individual noise sources on and off, we can choose which noise sources need to be turned on and off so that we can achieve specific compliance. So if this is the criteria line for receiver number 1, and this is the criteria for receiver number 2, and so on, receiver 3, receiver 4, we'll be able to dial up and down which noise sources get turned on and off so that we achieve specific desired percentiles of compliance at each receiver. We will be able to choose what percentage of received sound samples at each receiver comply with the criteria at each receiver. And this is what that looks like. So if we allow the computer to turn these individual noise sources on and off, if we use the evolutionary algorithm, it can do this many, many times and it can cycle through a huge number of possible options, and it can search through a vast solution space, turning individual noise sources on and off. It can choose which solutions achieve your desired percentile outcomes. You can ask the computer to please choose a good option, which sources to be turned off, so that you achieve a desired percentile compliance at each receiver. And if you've asked the Evolutionary Algorithm optimization method to maximize the number of noise sources that are on while we achieve that goal, then you have maximized the productivity of that mine or quarry or construction site, and you've deliberately chosen a percentage compliance to achieve at each receiver. So if we use our example noise sources and we asked the computer to achieve a target compliance of 90% at all of our receivers, then the evolutionary algorithm recommended that we turn off sources numbers 7, 8, and 9. And that is the maximum number of noise sources that can be on while still achieving 90% compliance at all of our receivers. So just checking, yes, we achieved at least 90% compliance at all of our receivers. And if we asked our evolutionary algorithm to achieve compliance of at least 95% at all of our receivers, then the method recommended that we turn off 4 noise sources. And in fact, this time it was the same 3 before receivers, sources 7, 8, and 9, and also now source number 5, and that does indeed achieve at least 95% compliance at all of our receivers. And if we asked the computer to achieve compliance of at least 99% at all of our receivers, then it recommends that the maximum number of noise sources that you can have on is the total number minus sources 7, 8, 9, 5, and 3. And that does indeed achieve the criteria for at least 99% of the time at all of our receivers. Well, what about the case where you have 50 noise sources? And each of those noise sources has a different sound power level, and each of those noise sources has a different standard deviation. So each one of these noise sources is uncertain and has a known amount of uncertainty because we know what the standard deviation is. Well, when we did that, and we asked the computer, please minimize the number of noise sources that you need to turn off in order to achieve 90% compliance at all of your receivers. We have 10 receivers this time. The computer said you need to turn off 12 noise sources. So that's the minimum number of noise sources that can be off in order to achieve the criteria. And we said the criteria is we want 90% compliance with our noise limit at all of our receivers. And if we ask the computer to choose the maximum number of noise sources that can be on while still maintaining compliance 95% of the time at all of our receivers, then the maximum number of noise sources that can be on is 50 minus 13. So it recommended that we turn off 13 noise sources. That's the minimum number of noise sources that you can turn off to maintain 95% compliance at all of your receivers. Now, Note that those 13 noise sources are not the same as the 12 noise sources before plus 1. And we do achieve at least 95% compliance at all of our receivers. So if we ask the computer to turn off the minimum number of noise sources while still maintaining compliance for at least 99% of the time at all of our receivers, then the computer says the minimum number of noise sources that you can turn off is 14. So these are 14 noise sources that are not the same as the 13 that we saw before, plus one more. These are 14 completely different noise sources, and we still maintain compliance at all of our receivers for at least 99% of the time. So if anyone has any questions, please feel free to post them in the comments below or contact me.